Loudspeaker impedance flattening? What is it? Why might we do it? And how do we do it? I'm Professor Fiore, and I'll explain it all to you immediately following our captivating title sequence. My, but that was captivating. Let's get into our loudspeaker impedance correction. What is the deal here? Well, simply stated, if you look on the back of a loudspeaker driver, it will typically say nominal impedance 8 ohms, or maybe 4 ohms. 8 being very typical for the home, 4 being very typical in car audio systems. In any case, the true impedance is a complex value, meaning it has both magnitude and phase, and that magnitude can vary considerably across the audible frequency spectrum. I'm talking about dips for an 8 ohm loudspeaker that might be around 4 or 5 ohms, and peaks that can be in excess of 30 ohms. Big changes. Now, why might that be a problem? Well, basically because it will interact with a passive crossover that you would use ahead of the driver. So when, let's say, a two-way system, you're going to have a woofer and a tweeter. A three-way, you'll also have a mid-range in there. But you're going to need some manner of splitting the frequency spectrum up. In other words, directing the content in those frequency ranges to the specific driver. That's what the job of the crossover is. Crossovers can be fairly simple, first-order units, second-order, third-order. They can be much more complex. The bottom line is, because we have a driver, the loudspeaker driver itself, having this variable impedance, this interacts with the design of the crossover. And that can lead to all kinds of odd aberrations in the crossover response. You can wind up with peaks and valleys of several decibels. Things that are clearly and obviously audible. So, you do your meticulous little design here on your idealized crossover with this idealized 8 ohm impedance. Then you throw a real loudspeaker on there and suddenly, your beautiful curve goes right out the window. Suddenly there's, a peak of 3 dB over here, and there's a dip over here of 5 dB, and then there's another peak at plus 3 or whatever the heck it is. So the way around this is to try to flatten the loudspeaker impedance. In other words, let's try to keep it relatively close to a specific value and keep the phase angle close to 0. Now, the closer we can get to this ideal flat impedance at purely resistive 0-degree angle, the better the results are going to be. But, even if we can't get it perfect, getting it better, right, will make things improved. So, how do we do it? Well, there's sort of two main things we're going to look at. On the high end, the response of the loudspeaker impedance is controlled largely by the voice coil inductance, and this will create a rise in impedance at high frequencies. At lower frequencies, there is a resonant hump. And for something like a woofer, this would occur at the free air resonance, FS. And that might be 30 hertz, 40 hertz, something like that. But that peak can be really quite high, 30, 40 ohms. So let's go look at a model for a loudspeaker. Now, I've gone through this little model here on a preceding video, and I have a link for it. It's in the AC circuit analysis playlist right after the power amplifiers, right after the series and parallel resonant section. But in any case, that video, if you've already seen it, this should look familiar. If not, and you want to develop your own model, that's a good place to start. But I'm going to give you a really quick overview of this. So, the real simple model is 8 ohm resistor. Not a good model. Not a good model at all. So we really have a number of reactive components in here. If you're looking at Thiel small parameters, what I'm calling RVC, which VC for voice coil. This is the resistance, DC resistance of the voice coil. And LVC is the inductance of the voice coil, because it is just a big coil of wire. And for the small parameters, this is called RE and this is called LE. Same thing. So what we're saying here is that resistance, if in other words, if you just got out a DMM and you stuck it on the voice coil, you'd get 5 ohms. And then if we measure the inductance in this particular model I'm using here, it's 1 millihenry. And then we have other elements out here. For example, this RES, this has to do with sort of mechanical leakages in the system. Then we have things like the suspension compliance and so forth, and those are modeled as capacitances and inductance, like springs basically. That's one way to look at it. And then there are other limiting elements on here. I have this RSH up here, which limits the high frequency effect of the inductor. Now there are multiple models that you can use of varying levels of complexity, but this is a fairly decent model. And I'll just tell you right off the top that LVC over here is what's going to control the high frequency impedance. And then this little parallel resonant thing right here is going to control the bass free air resonant mode. And the peak of that will largely be controlled by RES and a little bit of our voice coil over here. But basically, these two components over here are going to set that critical frequency, that resonant frequency FS, the free air resonance that you would see on a Thiel small parameter list. So let's run a little sim on here. What I've done is I've thrown in a current source, a 1 amp current source. Now, I know you're not normally going to drive a loudspeaker with a current source, but we're doing this on purpose because if I use a 1 amp current source, just think of Ohm's law, right? What's going to end up happening? V is equal to IR in DC, right? Or V is equal to IZ in this case. If I have a unity value of current, 1 amp, then the voltage I get is the same numeric value as the impedance is in ohms. So I can now just plot what the voltage is, and I'm going to see what the impedance looks like. So we'll just do an AC analysis over here, and that's it. Okay. Of course, when we do a Bode plot, this axis always comes up defaulting into decibels. So we do need to change this back into a linear. And I'm going to run this from 0 ohms up to 40 ohms, because that will capture everything. Okay, so here we have the magnitude of the resistance, and here we have the phase of the loudspeaker. So we see this starting off at a low value, right? This is a little over 5 ohms. If we went all the way back to DC, it would just be the 5 ohms. But this comes up to a resonant peak. And in this case, that looks like it's about a little over 70 hertz. And you can see the peak magnitude on that is up around 35 ohms. Then it dips back down. We get this sort of mid-range dip, which is back around 5 ohms again. And then this rise over here is again due to the inductance, right, the X of L of the voice coil. So what I would like to do ultimately is turn this thing into a nice flat straight line that's at 8 ohms or some other value, but a nice flat value. And the same thing with the phase shift. Notice the phase shift over here is swinging about plus and minus 50 degrees. It'd be nice if I could get it to hover closer to 0 degrees. All right, so the question then becomes, well, how do we do this? Because if you can imagine having a crossover, doing a calculation for 8 ohms, but then sometimes it's 30, 35, right? Sometimes it's 5. You can imagine that loading effect is going to really play havoc on the response of the crossover network. So we're going to do this in 2 parts. I want to take a look at a Zobel network, which is going to help us with the inductance. In other words, that high frequency bit that we see. So a Zobel is actually a fairly simple network. What I've done here is I have sort of 3 variations on the theme. I've got a voltage generator back here, so this is your amplifier. And I'm just going to use a simple first order crossover. In other words, just a capacitor in line. I assume this is going to be like a mid-bass or a mid-range driver. So I'm going to cross this using a nominal 8 ohms right here in the middle. This is our simplified computation. I'm assuming I've got an 8 ohm loudspeaker, and I'm going to have this system be critical at around 420, 425 hertz. Okay, that's what I'm looking at. So that, I conveniently chose a 47 microfarad capacitor. This is what I come up with. So we're going to look at what the ideal response curve is. Then we're going to compare that to our sort of vanilla loudspeaker that I'm using here. In other words, an uncompensated system. And then I'm going to use the same thing. So this is the exact same thing as this, but I'm going to add this little Zobel. So the Zobel is just a series RC network. And the idea is if I have a capacitive element, I can use that to compensate for an inductive element. Right? One is a positive phase angle, one is a negative phase angle. If I set them up correctly, they can cancel perfectly. I need the resistance in here because if I don't have the resistance, then the impedance, if I just put the cap over here, right, that's all I had, then the impedance would keep on falling as the frequency went up higher and higher and higher and higher, and we'd basically short out the power amplifier at really high frequencies, and we clearly don't want to do that. So the computation on this is fairly straightforward. There is an assumption built into this about where the voice coil starts to sort of take off. So the base value that's used is 1 1/4 times RE, or our voice coil. That's what you're going to use for our Zobel. And then there's a little computation over here involving the voice coil inductance and the resistance that you just came up with to get C Zobel. So what this is really doing in this case is it's sort of assuming a critical frequency of about 1 kilohertz, which is not a bad thing. And the equation just simplified. Instead of trying to figure out, hey, what is X sub C, at a certain frequency versus, this R value, they just simplify the equation into this. Now, I bring this up because if you look around on the internet, you can find plenty of sites, and I'm not going to go through it because they're out there, they're easy to find, plenty of sites that have Zobel calculators. So you just go there, you can plug these numbers in. It's a fairly straightforward thing. Like I said, you can get LVC and RVC off a Thiel small parameter spec sheet. It's RE and LE. Plug them in, boom, off you go. Right? So as the frequency goes up, this impedance starts to drop. At really low frequencies, this is an open and you can pretty much ignore it. And then when we get up, like I said, up to around 1 kilohertz or so, this starts to kick in and it starts to compensate for the inductive reactance of the voice coil. So let's see what we get. Now, we're going to look at 3 things here. We're going to look at the ideal response curve, right, a Bode plot for that. And this is first order, so this should be rolling off at 6 dB per octave, 20 dB per decade. Now you're saying, hey, I'm not going to use a first order. I'm going to use a second or a third order, or maybe something more complex than that. The reason why I'm using a first order is because this kind of spreads out the transition region and it's easy to see. I'm not suggesting that you should use a first order crossover. It's just that for our purposes, this is a really good illustrative tool. You'll be able to see exactly what's going on here very, very easily. Okay, so we're going to have the ideal, we're going to have our untreated loudspeaker, and then we're going to have the Zobel corrected loudspeaker. And we'll see what we get out of there. So again, we'll just do a little Bode plot. Alrighty, now I need, there we go. Okay, so this sort of middle green is the ideal. Okay, there I highlighted it in red. So this is what your basic calculation is doing. 8 ohms, 47 microfarads, 1/2 pi RC kind of thing. You come up with your 420 some odd hertz, whatever it was, I forgot. Let's see. Let's find -3. Right about there. Okay, so 422 and change. All right. Looks great. Just as expected. Now, this, right, which I've now highlighted as red, this is the uncorrected. This is the plain version, as I'm calling it. And you can see this is clearly not the same as the ideal green. And it makes perfect sense. The most obvious thing is this big hump down here in the bottom, in the base. That's because we had that huge impedance peak. Right? We had that big resonant peak around 70 hertz. So, you know, that this cap is not working against 8 ohms at 70 hertz. It's working against, you know, well, it's up here behind the graph, but it's working against, you know, 30, 35 ohms. So the amount of loss that you get is nowhere near the same. And we see this rise. So, you know, clearly we don't want that. All right. On the other hand, you know, compare that untreated version, let's call it that, to the ideal version. And up here, up around several hundred hertz, 1 kilohertz or so, there's a peak, right? There's an obvious peak going on here. And this is, again, because that impedance is starting to rise because of the voice coil inductance. So the amount of loss that we're getting, not so much. Let's see how big that actually is. That's coming up. All right, it's about 2.2, maybe 2.25 dB. Right, so that's, you know, not something we would want to see. So I've got this rise up here, you know, above, about an octave above the crossover. And then we've got this similar rise, you know, in the bass end, okay? Quick look at the phase response. We can say this is kind of funky compared to the idealized phase response. Now let's turn our attention to the Zobel corrected version, which is now the highlighted red one. And like I said, the Zobel is there to correct for the voice coil inductance, the high frequency end, and this is exactly what we see over here. All right, so this is bringing it down. We don't see the rise that we saw in the plain Jane version. It does create a little bit of a change down here in the bass, but you know, probably nothing to write home about. As a matter of fact, this area right in here, 200, 300, 400 hertz, is actually a little bit lower than we would like it to be. That actually made things a little bit worse. Now, again, if you had maybe a third order crossover, this wouldn't be quite so apparent. That's, again, why I'm using the first order here, so you can see all of this. Similarity in phase shift, you know, it's not like a huge improvement down here, but there is some improvement. So the Zobel does that one little piece of the puzzle, right? We have to like that. But, you know, you can't ignore the fact that there was this huge lump at the bass frequency because of the resonance, right? Because of the free air resonance. How do we fix that? Well, for that, same thing, by the way, right? Plain Jane, ideal, and now our corrected version. Here's the Zobel. I'm going to add an RLC series combo here. So if you think about a series resonance circuit, it has an impedance that's sort of U-shaped. At really low frequencies, the cap opens up, so we get a high impedance at low frequencies. And then at high frequencies, the inductor opens up, so we get a high impedance up there. And right at resonance, X sub L and X sub C cancel each other, and all we're left with is the series resistance. So we have this sort of U-shaped thing. Well, that's the inverse of what the resonant circuit over here is giving us. So if I can throw this in, that should compensate for this. So this is going to be resonant around whatever Fs is. And once again, you can go online and you can find calculators that will do this for you. So, you know, you put in like, you know, the RE value and the Fs value and a couple other things, and it'll spit out some values for you. And to be honest, that's exactly where I got these. Now, you could sit down and figure out what the critical frequency over here is. And then you just have to make sure that, you know, 1 over 2 pi square root of LC, this C and this L, works out to the same frequency. And then you can control the Q of that, right, how tight the curve is, through the ratio of C and L, right? You raise one and lower the other. So you might double this, halve this. It'll give you the same frequency, but all through the Q, right? So that's how you can kind of play with that. But in any case, you know, they'll go through and calculate this stuff for you. But I will tell you that there are assumptions made, and this is not necessarily perfect. So let's see what this little online calculator gives us. I'm going to do the same exact thing, do a Bode plot, see what we get. All righty. Where is our legend? Okay. So again, the green is the ideal, nice smooth curves. The plain is the maroon, and now our corrected version. Matter of fact, maybe I will change the colors on these so I don't have to keep highlighting them. Let's go blue on that. And let's see, we'll also do the corrected phase response. We'll turn that one blue as well. All right. Now, compare the blue to the untreated version and also compare it to the idealized case. So what we see is, all right, there's the Zobel effect up here, and we can see how this is, the series resonant has compensated for this. As a matter of fact, I would say it has overcompensated for it. Notice how this is dipping now instead of rising. So it actually went a little too far. All right. Also notice, by the way, that the phase response is, although not perfect, is a much smoother phase response than what we have from the unadulterated loudspeaker by itself. So this doesn't look too bad. This blue is definitely closer to what we want. As a matter of fact, if you look at it, it seems kind of like if we could shift it down a little bit in frequency, it would actually be closer. It's almost like, you know, instead of saying, well, I think we had like 420 some odd hertz, right? It's like this is, in a way, you could think of it as just being like a raised critical frequency. Okay, like the frequency has been shifted. So where's -3 for this? All right, close enough, right around there. Yeah, it's like 600 hertz. Now, if you could imagine pushing that down in frequency, maybe we could get something that's a little closer. In other words, a little closer to the ideal green curve. And that's easy enough to do. You can just alter the value of, in this case, this capacitor, right? You change the cap and you can shift this thing one way or the other. So what I did here is, you know, I noticed that, but I also noticed, hey, you know, this seems to be gone too far, right? Let's play with the series resonant thing here a little bit. I also don't like where the frequency, where it seems to max out over here, seems to be a little bit off. So what I did is I went through and tweaked these values a little bit. All right. See if I can come up with something a little bit better. So you can see I increased this cap a little bit, slight change on the inductor and the resistor over here. There's a little bit of a change to the Zobel. I brought this down to 5. And I increased the crossover cap to 63 microfarads because that's where I wanted to get that sort of shift in frequency response. Now let's check this one out, right? So this is the online version that has been tweaked. All right, let's see if we can improve on this a little bit. All righty, so let's see. Once again, let's change our colors over here. Olive. All right, let's see. Blue on that. Oh, I really should. I know it is consistent, but I really should come in here and get my little legend on there, so we have no doubts. All right, now compare the blue and the green, right? We've got you know, a couple dB of variation over here, right? This seems to be the worst part of it. Up here, they're pretty much coincident. They're coincident over here. There's a little bit of variation, again, maybe a dB or 2 over here. But pretty much that blue curve much more tightly follows the ideal green curve, right? Using our ideal 8 ohm resistance than, you know, the loudspeaker by itself, right? Compare the maroon to the blue and then compare that to the green. Wow, that's a nice improvement. And, you know, if we really wanted to fiddle with this, we could do a little bit better, I'm sure. But, you know, I'm really just trying to show you how this works. Now, also turn your attention to the phase response. So the blue is not perfect, but it does follow the idealized green curve much better, right? You don't have these big wide swings. This is really collapsed down. So, you know, theoretically, what we're saying is that the impedance of this network should be nicely flattened. And that brings up the question, well, just how flat is it? So, oops, hit the wrong button there, sorry. So here it is. I've taken that same thing and I've added on the current generator instead of the voltage generator so I can compare this to the very first circuit that we did. In other words, The very first thing was this part without the correction, right? We put the 1 amp current generator over here, and we plotted what the impedance was going to look like. So I'm going to do the same thing, and then we can just compare this to the original one. Let's see, I think I ran 10 hertz on that, if I remember correctly. All right, again, I have to change this into a linear from dB. And if I remember correctly, we ran from 0 to 40. All right. Okay. Well, that's pretty flat. And this phase looks really crazy, but, you know, this is only minus and plus 10 degrees. And if I remember correctly, I think the original one was 60 degrees. So let's do the same thing, and then we can compare apples to apples instead of oranges to kumquats. All right, so this is what we wind up with now, and this should be our first one. Yes, this is the very first one, right? Because it started down here a little over 5, went up to about 35 ohms, came crashing down, and then took off on the top, and we had this like plus and minus 50 degree phase shift change, you know, this big huge sweep over there. So this is what we start off with. This is what we end up with. Is this perfectly flat at 8 ohms? No, it's not. Is this perfectly flat at 0 degrees? No, it's not. But it's a heck of a lot better than this. Okay. And as I said, you know, the proof is right here in the response curve. You know, that blue curve is what makes everything. You know, that's just beautiful. Okay, so final closing thoughts. We see that it's possible using the Zobel and a series resonance circuit to flatten out the impedance curve of a loudspeaker. And if we do that, the loading effects on the crossover network are minimized, and we wind up with a much more well-behaved, much more ideal response curve in terms of both magnitude and phase. This, however, does not come out free. You know, there are downsides to this. The obvious one is the increased number of components. So we have increased cost and circuit complexity. Some of those, depending on the frequencies you're using, might be fairly large. You might have to use a very large capacitor, inductor. You know, those things take up a lot of space. They're expensive, right? Those are things to consider. And of course, there are resistors in there, and there's going to be power lost in those resistors. So that is going to tax your power amplifier a little bit more. And what we're looking at is just a simple single driver. But of course, you know, there's a complicating set of factors here in that, you know, you have a two-way or a three-way system. So the interactions become greater, and you also have to consider things like, well, how does the impedance change because we put this thing in a box? You know, if we look at a woofer and you put that into a sealed enclosure or a vented enclosure, that changes the impedance curve. There's a fairly dramatic change in the low frequency end. So that's another thing that we have to consider. All right. It's definitely an improvement if you're going to ignore the cost and complexity stuff, right? But it's definitely an improvement. Is it the best we can do? No. It's not the best we can do. As a matter of fact, I am a proponent of throwing all of this away. To my mind, the best thing to do is just dispense completely with passive crossovers and go to an actively crossed system. In other words, coming out of your amplifier, your preamplifier basically, you would go through an active crossover, and I have several videos on active crossover designs in the op amps playlist, but that would divide out the spectrum into, you know, 2, 3, however many pieces you want, using low-level signals, using things like operational amplifiers, and then those separate outputs go to their own power amplifiers, which are then directly connected to the drivers. So if you had a two-way system, coming out of your preamp would be the crossover, and there would be two outputs. There'd be a treble output and a woofer output, or a bass output. Each one of those goes into its own amplifier. So there's a tweeter amplifier and there's a woofer amplifier. Now, the amplifiers are connected directly to the loudspeakers, so there's never any issue with, the interaction between the crossover and the loudspeaker impedance. Right? That's a direct connection, and the power amplifiers themselves are treated as ideal voltage amplifiers with very, very, very low internal impedance. It's the greatest thing going. Right? That's really the way you would like to do it. It is, of course, a more complicated and considerably more costly thing to do. So, okay, if you're sitting around in your room, right, your home, whatever, a passively crossed system, you can get really nice results out of a passively crossed system. But if you're looking for high output power, the absolute lowest distortion, you're really pushing the envelope on performance here. If you're in a recording studio, right, you're doing PA work, stuff like that, you want to go to an actively crossed system. They have proven themselves over and over and over. And really, that's what I would do. Okay, that's where I would go for that. I have plenty of passively crossed loudspeakers kicking around my house over the years, but I've also worked with, actively crossed systems, and ultimately they can't be beat. So, you pays your money, it takes your choice, right? Well, I hope you've gotten something useful out of this. And until next time, this is Professor Fiore saying, take care.